Topic 5, Part B. What is RTL? We know what is RTL. RTL has sequential components, combinational components. RTL has a sequencer, which is a sequential component. We are not concerned about this, but we know that they exist, and we will eventually get to those. For now, RTL data path has certain combinational components. Okay, these combinational components are things like decoders, multiplexers, a parity circuit, an adder, a comparator, a circuit that does multiple of things. And what we are doing now, we are learning these. What are we learning about these? What we are learning about each one of these is, so we're going to go through each one of these, right? But then what we are learning is, one, functionality. Okay, well, an adder add, so its function is add. Okay, 2, the hardware of it. Okay, so if I show you an adder, I have to show you the hardware, and hardware is at the gate level. Okay, that's because the same way I showed you gates in terms of transistors, now I'm showing you an adder in terms of gates. Okay. 3, maybe I design a 4-bit adder. I want to show you, I have to show you, what if I want to take this unit, this 4-bit adder, and cascade it. So cascading is something I have to show you. To build a 16-bit adder out of 2 4-bit adders. What else I want to show you? I want to show you if I have a certain circuit, let's say a comparator, that has an output that becomes 1 when A is greater than B. What if I want to configure it so that the output becomes becomes 1 when A greater than or equal to B? Okay, so certain configurability in in certain components is needed, and they exist. Or for example, what if I design a comparator which is a unsigned number comparator, but then somebody else needs a 2's complement comparator? What do? Well, I configure it so that that certain comparator, without going into the complete doing the comparator, I want to make it a comparator that compares to 2's complement numbers. Okay, so configurability in certain components is needed. What else I want to show you? I want to show you a very important thing, the Verilog description of whatever I present. Remember, when I showed you an NMOS transistor, I showed you NMOS Verilog description of it. Then I put 4 transistors together, 2 NMOS, 2 PMOS, NMOS transistors connected to ground, PMOS transistor connected to supply. I made an AND gate, and then what did I do? I showed you the Verilog description of the NAND gate. I also showed you an assign statement, a different way of writing an a NAND output. Okay, tilde A, B. Okay, well, here I'm going to do the same, because I may have a way of writing a decoder. Maybe I have a different way of writing it. Maybe there is one that is more compact. There is one that is more flexible. There is one that is more expandable. Okay? So these are what we will be showing. Okay? And I didn't say anything about application. Okay. Throughout, we will learn new Verilog constructs. So far, what we have learned with Verilog is we have transistor instantiation in MOS. Optionally, 3 timing values, 5, 7, 9. Okay. An optional instance name. The output, W. The input and the gate control. Then I also showed you NAND gate. 2 delay values, 12 and let's say 15. U11, for example. The output, the A input, the B input, the C input, the D input. I can have an AND up to this. Or I also showed you a way of writing a Boolean expression, a sign, and sharp sign, 25, 31. Because it's getting more complex, I give it more delay. If you don't want to give it delay, don't. Okay. And then here you say W equal, okay, put any Boolean expression you want, A XOR with B, perhaps ended with C XOR with the D, ended, or with something, something, something. Okay? It's not, this is vertical bar. All right, these are the Verilog descriptions we have learned so far. And we have also learned how to wire these together, which we're going to be seeing a little bit more of. All right, so this is what my target is. And let's start with the very basic component, which is called a decoder. A decoder decodes. Okay, it takes its input, decodes, opens it up. There are various decoders. There's a decoder that takes a binary number, turns it into a code for driving these 7-segment displays. This is called a 7-segment decoder. Okay. There is a decoder that takes a binary number, opens it up so that you can tell that what number it's representing. See, if I give you 00 and tell you this is a binary number, you have to have a knowledge of binary system in order to be able to decode this, to understand that this is 0. If I give you 10 and tell you this is binary, you have to have the knowledge of binary system so that you say, okay, this is 220, this is 221, let's add these together, this is number 2, and therefore you say, okay, this is 2. If I give you 11, then the same thing. You have a knowledge of that, and then you are able to decode that and tell me this is a 3. Okay? I'm going to build a circuit that takes these coded numbers. See, these are coded numbers. Takes these coded numbers and opens them up, meaning that it has 4 outputs, one representing number 0, one representing 1, one representing 2, one representing 3. These are the Y outputs. And then this is the AB input. If I give it 2, the light connected to output number 2 will light up. If I give it 3, binary 3, the light connected to the light bulb connected to output 3 will turn on. Therefore, I say that, okay, this is not coded anymore. It's clear. There are 4 light bulbs. Number 1 or number 2, number 3 or number 4 turn on. If I'm able to design a circuit like this, I call this one binary 2 to 4 decoder. Or maybe a binary 3 to 8 decoder. Maybe a binary 16 to 64,000 decoder. Or maybe I can design a binary 2 to 4 decoder, and then later I cascade this to form a binary 3 to 8 decoder. Cascade those to make it a 4 to 16 decoder. Okay? This is a decoder. Let's build it, but then how do we build these things? The same way I use transistor to build gates, I'm going to use gates to build decoders. So I'm going to build this. Okay, I'm going to build this, and the first thing I think is, okay, I have A1, A0, and A1 is my most, A0 is my least significant bit, and 0, 0, I0, output 0 becomes 1. That means, okay, the 0, 0 was decoded into output number 0. 0, 1 decoded into output number 1. 1, 0 decoded into output number 2. 1, 1 decoded into output number 1. The thing is, if I were to build this, which I'm going to be doing right now, the gates that are available to me are NAND gates, NOR gates. Okay, let me go back to this slide here. So if I start building this, I say, well, okay, let's put A1 here, A0 here, and let's put 2 inverters here. And if A1 is 0 and B1 is 0, then this I0 becomes 1. If A1 is 1, A0 is, if A1 is 0, A0 is 0, is 1, then I1 becomes 1. Okay, so this circuit that I'm showing here, that the truth table of which I'm showing here on the left, can easily be built using AND gates. But then I go and look at my other bag, my gates bag. And I find that the gates that I have been able to build using transistors, they all have NMOS transistors at the bottom and PMOS transistors on top. What it means is the gates that I have are either NAND or NOR. I don't have an AND. If I want to have an AND, I have to take a NAND and put an inverter on it. That's not good, because if I put an inverter on the output, that gives me 2 more transistors. That gives me more delay. Okay, I can do that. I can build I can put an AND here and put an inverter here, and therefore I will have the table shown on the left, lower left-hand side. But then I'm going to do something different. Okay, so here is my NAND gate. A, B, NAND. I'm going to do something different. I'm going to say, well, instead of taking the NAND and then inverting it, why don't I just change the meaning of the output? Instead of saying the light turns on when the output becomes 1, I say the light turns on when the output becomes 0. Okay, so instead of saying that I have a decoder with active high outputs, these are active high outputs, I can just say, well, let's not put that inverter on the output. Let's keep the NAND as is. Okay, let's don't turn the functionality of it into AND. Let's keep it as NAND. Just change your wording. Change your wording. Say that, okay, since the only gates that are available to me are NAND and NOR, okay, I'm going to do this. A1, A0, build this. A1, A0, 1, 2, 3, 4. See, here is an AND. Okay, I'm going to use 4 NAND gates. 0, 0, 0, 1, 1, 0, 1, 1. Okay? If I put inverters, it becomes the table on the left-hand side. Active high outputs. I'm not going to put inverter. Once again, because putting an inverter on this output means that I have to have these two transistors also added to each of these outputs. I don't want to do that. Why waste two transistors? Not only that, why waste a delay from NAND to transistor? So my circuit not only has two more transistors, but it also has longer delay. So what do? I say, well, this is good as is, except that my outputs are active low outputs. Okay, active low outputs. That's all there is to it. Don't say it's active high output. It's like a switch. When you move it up, the light turns on. Or maybe there is a switch which is reverse. When you move it down, the light turns on. Then you turn on the light. Doesn't matter. If it requires less hardware, turn it around. Okay? And just change the definition of your circuit. Say, this is a decoder with active low outputs. And then put a symbol there to indicate that this is a decoder with active low outputs. Okay? Because nobody's going to look inside your decoder. You have to clearly tell the person using this circuit that it's a decoder with active low outputs, and therefore you put bubbles on the outputs to indicate that this is active low. These are active low. They don't require this inverter. The output is taken directly from the NAND. And the symbol for it is this bubble on the output. If there was no bubble, you would be talking about the table on the left-hand side. Now that there is a bubble, you are talking about the table on the right-hand side. That's it. That's it with the base of my decoder. Okay, that's a 2 to 4 decoder. So I start with a decoder like that, and I have this wrong everywhere. I start with a decoder like this, which is a 2 to 4 decoder, active low output, and once again look to see if I have one input, outputs 0, 2, and 3 are not active, they are 1, output 1, which corresponds to the binary equivalent of A1, A0, that is 0 or is active. Okay, so I did my decoder. But then I get to this point saying that, didn't I say that I like a decoder, that I like it to be cascadable, so building a larger decoder. This decoder, the way I build it, doesn't qualify for that. So what I do is I add an enable to it. For now, let's not worry about how this enable is going to make this unit cascadable. Let's talk about the definition of enable. An enable input works like this. If the circuit is enabled, the outputs are active according to what the input is. Okay, that means what the inputs are. For example, if the circuit is enabled, A1, A0 is 1, 0, that means number 2. I2, which is output 2, becomes active. That means this becomes 0, the rest of them become 1. That's if the circuit is enabled. If the circuit is not enabled, all outputs are going to be non-active, inactive. Okay? Meaning, if the circuit is not enabled, all of these are going to be 1s. So, how do I build this circuit? I already have 2 input NAND gates. All I'm going to do is I'm going to add a third input to these NAND gates. If this input is 0, the circuit is not enabled. All the outputs are inactive. That means they are 1s. If enable is 1, then the circuit is enabled. Okay? My outputs are active low. I'm going to do something different now. I'm also going to make my enable input active low. There are electrical reasons for it. There are also logical reasons for it. The logical reasons is, since my outputs are active low, if these outputs are going to drive enables of other decoders, in that case, the active low output and the active low enable will match, and I don't need extra inverters. We will see that in a few minutes. Okay? For now, take it from me that I'm going to add an inverter so that I make my enable active low. Now let's look at the table of this green circuit on the left-hand side. This is the functionality of it, and the symbol I have up there is the notation for it, because people don't want to go into all these gates. All right, the circuit says this. The circuit says if enable is 1, that means the circuit, if it is, this is wrong. If enable is 0, okay, the circuit is working. If enable is 1, A1, A0, no matter what they are. If enable is 1, look, if enable is 1, if there is a 1 here, there is a 0 here, a 0 on the AND gate inputs makes all of these the NAND gates 1s, and therefore if I have a 1 on enable, all my outputs are going to be inactive. And if my enable is 0, only then you're going to be looking at A1, A0, A1, A0, 0, 0. This is going to be active. Okay. No. This is going to be active. The rest not active. This is going to be active. The rest not active. This is going to be active. The rest not active. Active. The rest not active. Okay? Which is the table on the right hand side. All right. I will make a correction of this in the annotated slides. The symbol for it is the symbol I'm showing up there. It has an active low enable, active low enable, and 4 active low outputs. How do I know how do I know without looking into it? Well, I know because I have a bubble. A bubble means active low, both on the input and on the output. So I've shown you the functionality and the block diagram of it, and also the circuit inside it. This is a much larger decoder, and this is a 4 to 16 binary decoder. How do I build a 4 to 16 binary decoder out of smaller decoders? Okay, don't look at the right hand side, only listen to me. 4 to 16 decoders. A 4 to 16 decoder. How many outputs you have? 16. The only component I'm giving you is this, a 2 to 4 decoder. A 2 to 4 decoder gives you 4 outputs. Okay? What I'm requiring you to do is to put together 2 to 4 decoders to build a 4 to 16 decoder. This is what I'm requiring you to do. Then you say, well, the components I have, each one has 4 outputs only. I'm required to do 16 outputs. So what do? I put 4 of those together. 4 4s, that gives me 16 outputs. Let's live with this for now, and then we still have work to do. So I put 4 of these and say, well, okay, this is giving me the 16 outputs that I want. All right. That's as far as the output. How about the inputs? The inputs, each of the 2 to 4 decoders has 2 inputs. But then a 4 to 16 obviously has 4 inputs. So you take the least significant bits of the 4 inputs. That means if you are having A3, A2, A1, A0, you take A1 and A0. Okay? You take A1 and A0, give A1 and A0 to all of your 2 to 4 binary decoders as you are seeing on the right-hand side. So I take A1 and A0 and give it to all 4 binary 2 to 4 decoders that we decided that we want to have. And then I say, well, if A1, A0 is 0, 0, all 4 of them are going to make their output I0 active. All 4 of them at the same time. Okay? If it's 0, 1, all 4 of them are going to make their I1s active. Okay? If it's 0, 1. If it is 1, 0, all 4 of them are going to make their I2s active. And Now that we have done this, we have gone this far. If this is 1, 1, then all 4 of them are going to do the I3 is active. But see, I don't want that. I don't want all 4 of them to do the same thing. What I want is, I want A3, A3 and A2 to decide which one of these 4 is going to be active and which ones are not going to be active. Remember, I put an enable here. The enable takes the entire decoder, deactivates it. Okay? So I say this. Let's take A3 and A2. Let's take A3 and A2. Connect those to a new decoder. A 5th 2 to 4 decoder. Okay? If A3, A2 is 0, 0, the upper input of this binary 2 to 4 decoder is active. Okay, so let's do the same thing here. If this is 0, 0, 0, 0, this is going to be active. Notice that when I say active, I don't put a value. It's important that it's active. Okay? If it's 0, 1, this is active. If it is 1, 0, this is active. If it is 1, 1, this is active. If the light green is active, it is connected to the active low enable input of the upper right hand side decoder, and then that light green output itself is active low, and therefore if I have 0, 0 on A3, A2, the upper right hand side decoder will be active. No, I want a different color. The upper right hand side decoder will be active. This one will be active. And therefore, only that is going to be looking at A1 and A0. And according to A1 and A0, it's going to be making its output active. What happens to the other 3 below that? The other 3 below that are all having an enable of 1. Enable of 1 means they are not enabled. And therefore, all of these outputs are going to be 1s. Only the upper one. And the upper one, according to A1, A0, that one output is going to be 0. 15 other outputs are all going to be 1s. And then, if I have this situation, 0, 1, okay, 0, 1, so 0, 1, only this is going to be active. Okay, that means I0, I1, look at this. I0, I1, I2, I3, I8, 9, 10, 11, 12, 13, 14, 15. These are all going to be 1s. I guarantee that. I guarantee these are going to be 1s because only the black check mark is active, and the black check mark is going into the second from the top binary decoder. And that binary decoder has, depending on A1, A0, if it is, let's say, 1, 0, only this is going to be active. Everything else will be inactive. And therefore, what I just built is a 4 to 16 decoder. Not only that, because I have an enable input, my 4 to 16 decoder has an enable input also. What did enable input give me? The enable input gave me the opportunity to take these decoders and cascade them. And therefore, if you have a 6 to 64. Okay, 6 to 64 decoder. You take 4 of these, 6 to 64, that means you have 6 inputs. A5, A4, A3, A2, A1, A0. Okay? 6 to 64. You take A5 and A4, give it to a 2 to 4 decoder. That 2 to 4 decoder will be selecting one of these 4 to 16 decoders. Okay? And therefore you have a cascaded higher decoder. Okay? So you can build any size decoder. Any size decoder you want. I promised you that I will also give you the Verilog description, but before that, let me say something. See if I want to build a NAND gate, a 2-input NAND gate, I build it like this. If I want to build a 3-input NAND gate, I can go to the transistor circuit, put 3 transistors NMOS in the lower side, and then 4 PMOS in parallel in the pull-up side. Okay. If I want to do a 4-input NAND, 1, 2, 3, 4, I do this, and then I gave 4 transistors there. If I have only 2-input NANDs and you tell me you really want a 4-input NAND, I have to do this. I have to put an inverter here and then put a 2-input NAND here and then put another inverter here and then put another 2-input NAND. I'm still able to give you a 4-input NAND, but with more number of transistors and much longer delay, because I'm going from here to here to here to here to here before reaching the output. Whereas if I were able to do 4 transistors in series, I'm not saying the series transistor, 4 of them, is going to have the same delay as a 2 transistor circuit, but then the 2-input NAND gate, but then the delay is not as bad as the cascading that I'm showing on the left-hand side. So what I'm saying is cascading is good because you take one small circuit and build bigger and bigger and bigger and bigger. There's no limit to it. But then there is a price to pay. There is no free lunch. There is a price to pay. The price you are paying is that you are getting a longer and longer and longer delay. Look at this, for example. The circuit I built over here, okay? There are 2 logic levels in each of these binary decoders. So going from the A3 all the way to the outputs, you have 2 logic levels here, 2 logic levels here, and therefore you have a delay of 4. 4 gates. If instead of doing this, you had gone to this green circuit and added your A3, A2, and just expanded it into larger NAND gates, this circuit would be a 4 to 16 decoder with much smaller delay. Okay? So cascadability is good, cascading is good, but then it keeps adding more delays. Sometimes you have no choice. Sometimes the only gate you have is a 2-input NAND gate, so live with it. Cascaded if needed. Sometimes the only decoder you have is a 4 to 16 decoder. And then if you need larger decoders, you have to take this 4 to 16 decoder and build larger ones by cascade. So this is explained. This is cascading adds delay. Both in ANDing and also in decoding. Let's do the Verilog description of this. I have a 2-input select input, which is I have a 2-input A, which is the binary number. I have an enable, and the enable is active low. I show you why active low. And I have 4 outputs, which are I0, I1, I2, I3. I'm using an assign statement, and I'm using a condition operator. Condition operator. Condition operator works like this. Condition, then expression 1, else expression 2. But then you can say, instead of expression 2, you can put another condition, condition 2, then expression 3, else, instead of putting expression 4, you can put another condition, and on and on and on and on until the very last case that you cannot put any more conditions. Okay, at one point you have to end. You cannot go on forever. The very last one has to be without any condition. I'm going to show you the example here for the 224 decoder. Assign I, the 4-bit I. Something I'm showing you here, which is new, is vector declaration. I've shown you A and B declaration for the AND gates. I'm showing you here vector declaration. Verilog, when you are declaring vectors, it goes into square brackets. When you declare your inputs and you want to have 2-bit inputs, you say input 1:0. That gives you 1 is the leftmost, 0 is the rightmost. And then A. If you have another input, let's say A, comma B, comma C, until the next word or the next keyword input, okay, everything will be governed by this decoding, by this indexing here. And then I have input enable. That means this is a 1-bit input. Output 0:3. That means the leftmost is 0, the rightmost is 3. Okay. Assign I is, if enable is 1, my output becomes 1, 1, 1, 1. This means that this is active, low, enable. That means enable high is inactive. Outputs are 4 ones. That means these are also active, low. Okay. Then that's a condition. I'm saying if enable is active, if enable is 1, the outputs are all 1, not active. Else means, okay, what's the condition here? The condition was enabled. Else means the enable is 0, means active. Okay, now we are talking. Now we are talking. Meaning what? Meaning enable is active. Okay. Now we are talking, which is enable is 0. When enable is 0, if A is 0, 0, okay? A is 2-bit, I'm using the number 0. If A is 0, 0 binary is 0, 0. If A is 0, 0, I am putting the following string on the output. This is number representation in Verilog. The string is 4 bits. 4 bits. The number of bits I'm writing are 4. A single quote followed by B is binary. The number I'm going to put is a binary number. 0, 1, 1, 1. Okay? So The way it works is you put the size there. 4 is the size. Single quote. Hex or B or decimal. Okay, here I'm using B for binary. And then put the corresponding digits. If it's hex, you put F. For this one, 0, 1, 1, 1. What is 0, 1, 1, 1 in hex? Is 7. Okay, so you are saying 4, hex digit, 7. Therefore, you take 7, turn it into a 4-bit. Everything turns into bits. Okay? And so you say 4H7. That means this is a hex number, 4 bits, and then the number is actually 7. So here I have, if A is 0, I'm putting 0, 1, 1, 1 on the output. If A is 1, I am putting binary 1, 0, 1, 1 on the output. That means the output number start from the left-hand side. See, this is 0. So bit number 1 is active. If A is 2, 1, 1, 0, 1, that means bit number 2 is active. And if A is 3, I am putting 1, 1, 1, 0 on the output. That means bit number 4 is active. Else. See, these are all if else's. The very last else says if none of these, then put 4 X's on the output. Okay, X's means, remember in the case of transistors, X's mean that they are conflicts. Okay, but X also has other meanings. X means invalid. X means uninitialized. X means unknown. So what I'm saying is, if none of these, then I don't really know what to put on the output, so I put 4 X's. But I don't really expect and none of these to be true. If I have a 2-bit number, I at least want to have the 2-bit number being 0, 1, 1, 0, 1, 1, 1, 0. Okay? All right, so this is the Verilog description of it, using assign statement, using condition operator. If you wanted to, you could go back here and describe each output using the NAND functionality of it. You could do that. You could write this NAND circuit completely as is here, okay, using NAND primitive. NAND primitive means this is a NAND primitive. So you would do I0, okay, is the output, and then you would put this input, and then you would list them all out. Or you could do individual assign statements. But then I'm using what is referred to as condition operator, which is this, which makes life a lot easier. All right, what else? Memories use decoders. Okay, so I have a processor that is trying to access a large memory, but see, I don't have a large memory. I have segments of memory. I have pieces of memory. Let's say I have 8K memories, 8,000 bytes of memory. But then I want to have, let's say, a 64. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Right. I have 8K blocks of memory, and then I want to build a 64K memory. What I do is I take a address decoder, 3 to 8 address decoder, exactly as I did with the cascading there. I take the 3 most significant bits of the address, bits 15, 14, and 13, put them into the address decoder, okay, and then according to 15, 14, 13, one of these outputs is going to be active, and then the output that is active is activating the corresponding block. And then each block is taking bits number 12 down to 0, these 13 bits for 8K bytes of memory. Each block of memory is taking 13 bits, and these three last most significant bits are selecting the blocks of the memory. All right, enough of decoder. The next is multiplexer, and we're going to do the same thing for the multiplexer, okay, which is functionality, hardware, cascading, configurability, Verilog, and application. The clock rings. This is the end of decoder.